Cool. Well, then, yeah, welcome everybody. I'd love to introduce Lily Zhu from Columbia University, and she's been, trying to understand the action side of conservation and natural impact to figure out what we're actually do about it and kind of with how to make rational decisions. So, yeah, welcome, Lily.
Fantastic. Thank you so much, Greg. And it's really exciting to be here with all of you. And I know that Google has a lot of wonderful initiatives in nature and climate. So I'm happy to see this series thinking about the technical challenges behind some of this work. And as Greg mentioned, I really focus on after we've developed some model, how can we take that model and actually design more effective interventions? So that's what I'll be talking about today with a focus on wildlife conservation. So as we are all aware, our planet is facing many global challenges, from biodiversity loss to climate change, public health issues, including maternal mortality and food insecurity. And importantly, all of these challenges are interlinked. So biodiversity conservation, for example, is an essential solution as part of the climate change mitigation and adaptation strategies. So nature-based solutions can contribute up to 37% of the CO2 emissions necessary to meet the Paris Agreement and halt global warming. Meanwhile, climate change is currently exacerbating biodiversity loss by stripping species of their climatic habitat range, forcing them to move and adapt, but oftentimes they aren't able to adapt as quickly as necessary. So I'll focus today on the biodiversity crisis and just a few statistics to get a sense of this problem. We've experienced a 70% decline in the average population of mammal species in the last 55 years. And there's currently an estimated 1 million species in danger of extinction out of only 8 million species on this planet. So it's a very large-scale problem. And biodiversity, aside from helping with climate mitigation, is also an essential factor for human health and food insecurity. So really, these are interlocked challenges. And fortunately, to kind of meet the moment and respond to the urgent and rapid losses that we're experiencing, there has also been a large amount of international agreement and mobilization towards addressing biodiversity loss. So in 2022, we had the kind of nature equivalent of the Paris Agreement, where 196 countries around the world signed the Global Biodiversity Framework, committing to a large number of things. And one of the key provisions of the Global Biodiversity Framework is known as the 30 by 30 initiative, which is the commitment to increasing the amount of the world's protected lands and oceans to 30% by 2030. So this is over a doubling of the amount of the world's protected land and over a tripling of the amount of the world's protected marine area. But unfortunately, even currently protected areas face large threats. So this is an article from The Guardian of Murchison Falls National Park in Uganda, which is a site that I've been working with for many years. And this is a photo of a team of rangers in front of this mountain of snares that were found in Murchison Falls. So every single one of these little wire circles corresponds to an animal life that could have been lost. And there's an estimated 4 snares for every square kilometers in the park. And this is a very large park, about 5,000 square kilometers. So that's nearly 20,000 snares that are present in Murchison Falls, each of which could catch an animal. And unfortunately, there's only 250 rangers available to conduct patrols and allocate resources. So it's a huge challenge of limited resources and determining where to best send our interventions. So my research focuses on helping rangers plan patrols to more effectively prevent poaching. And across the spectrum of work in resource allocation for conservation and other environmental challenges, there's many stages, and oftentimes this will come with learning. So machine learning to try to understand what is the state of the world, where are threats, where are things changing. We need to do planning techniques. So bring in AI tools like reinforcement learning for policy decisions, and operations research using post optimization to determine where to send resources and think about sequential planning over longer time horizons. After we've taken some actions, we want to understand what the impact of that action was, ideally with causal inference, to understand which actions are most effective and what should we continue and what should we stop doing. And then also working with partners to deploy these tools at scale. So my research and what I'll present today is kind of an overview of the whole parts of these pipeline, starting from machine learning with online learning for proactive data collection, moving to reinforcement learning for robust planning, and also think about causal inference. And I'll talk a little bit about work on generative AI at the end as well. And what I hope to emphasize is that developing novel methodology is necessary in order to address the types of challenges that we're facing in these settings. And that can also be paired with impact, because now we're creating new abilities that weren't possible with previous tools. And a key component of my research is doing very grounded work in close partnership with stakeholders. So I've had the privilege of going on field visits to sites across Cambodia, Belize, and Uganda, and just working closely with the people who are doing the important work on the ground there. So first, I'll talk about this work on multi-armed bandits, and I'll ground us in the context of Sripak Wildlife Sanctuary in Cambodia, which is home to many species, including endangered elephants and clouded leopards, which are all unfortunately threatened with poaching. So the data that we have and the action that we're taking is trying to determine where to send rangers across this large protected area. And here we see a map of historical ranger patrols. So this is visualizing 6 years. And we can see that even across 6 years of patrol, there are many areas of the park that have never been visited at all. So it's a large park. We only have so many resources, so they'd have to just kind of concentrate their efforts. And in the observational data that we have, some of these observations are also tagged not just with a GPS coordinate, but also with a sighting of biodiversity or a poaching activity of threats like a snare or ashes from a poacher's campsite. And the question that we have is, how do we translate the historical observations to inform future planning? And we set up this problem by first discretizing the space into some N regions. And we have some associated covariate vector for each region. So that comes from geospatial information about plant cover, rivers, how far we are to the nearest river, elevation. We have human information, such as how far are we to the nearest human infrastructure, like roads or villages. And dynamic information that changes over time, coming from publicly available remote sensing sources. And this gives us the ability to capture seasonality and look at changes over time from, for example, shifting climate. And our goal is to determine some action, which is allocating a series of patrols to some subset of regions. So we have N regions that we want to send rangers to, and we have a budget constraint, such as 40 hours per week that they are able to spend out in the park. And our goal is to maximize the expected number of snares removed. But the challenge is the expected number of snares is unknown. We don't know exactly what poacher behavior is. We only get these like very noisy samples from what rangers are able to detect. And before going into to how we formulate this as an online learning problem with bandits, I'll go back to some earlier work on just bringing in supervised learning here. So this is starting with the patrol data that we have. We can see for each place in the park, each 1 square kilometer region is 1 pixel. We can determine the total amount of patrol effort that was spent there over a month or some series of time. And we can also observe the poaching activity that was detected in that region. We combine that with the geospatial information, and we can use that to predict the probability of poaching in the future. And this is slightly older work, so we were using Gaussian processes and developing an ensemble model to address imperfect observation, but I won't go into detail about that. And we were also really interested in understanding how these predictions translated into actionable insights on the ground. So in order to evaluate the performance of our model, not just in terms of AUC, but also in terms of observable differences on the ground, we conducted a series of field tests over the course of 5 months, where we took our predictions, identified a series of areas that we predicted to be high risk of poaching and medium and low risk, and asked rangers to patrol those areas for a month at a time. And to keep this a valid experiment, we kept it blind, so they weren't informed of the risk classifications in advance. And we also focused on areas that were infrequently patrolled in the past, so we weren't just relying on historical patterns. And rangers patrolled, and indeed, they found many more snares in the areas that we predicted to be at high risk than medium or low risk of poaching. And then in a single month, when we were focused on having them patrol high-risk areas, they found over 1,000 snares, which is about a 3-fold increase over typical patrols. So we were really excited about this result, and we were thrilled to get positive feedback from our collaborators at WWF, who said, I'm super excited about the results, and let's scale this out to other countries. So I spent a lot of time working with SMART, which is a consortium of 8 different NGOs, on integrating our predictive models into an existing software system that they use for protected area management. So the observations that rangers track are stored on this database system known as SMART, and we integrated our predictions as a plugin onto the system so that people were able to generate their predictions on their own without having to go through us as an intermediate. And SMART is one. Yes, Greg?
Just to understand the kind of setting, you're given the patrols that happen, you're trying to predict the effectiveness of the patrols. But the data set, just visually speaking, seems highly biased. They seem to follow tracks, rivers, logical places. Yes. So how do you undo that bias?
Yes. So I will talk a lot about imperfect observation. So
awesome. Thank you.
Okay, so right now we're just focused on the predictive task of predicting where poaching hotspots might be based on historical observations. And one of the inputs into this predictive model is looking at the amount of patrol effort. So it's looking at how much time or distance they cover in a specific area, and that gives us a little bit of information about the amount of effort necessary in order to find snares. And then we make predictions on if they were to patrol a certain amount, if they were to spend a certain amount of effort, here's what we would predict. But then I'll talk about the variety of other tools that we throw in for this. So SMART is widely used by protected areas around the world, and some of them, like Sripak, have relatively plentiful historical observations, but others of them are just beginning to collect data. They're only getting set up with a SMART system now. So I was speaking with protected area managers in Malaysia at Royal Balloon State Park, and they were really interested in getting more informed predictions and recommendations for how to strategize their patrols. So I said I'd be really happy to work with them, and they shared their data. But unfortunately, the data was extremely sparse. So they only had about 3 months of observations, and much of the park had not been patrolled previously. So this is just not enough information to build a supervised learning model. And what we focus on there is recognizing that for these data scarce parks, we have to think about how to conduct patrols to simultaneously detect poaching activity while also improving the predictive model. And that requires us exploiting areas where we have a lot of information, we have a good understanding of the system, but then also exploring areas with high uncertainty so that we are getting adequate coverage throughout the space. And many of you might recognize this as a paradigm for online learning, which led us to a multi-armed bandits approach. And to just give an overview of very quickly about multi-armed bandits, it's thinking about how do we take actions where at each time step, the action that we take gives us information that we're discovering about the expected reward from that action, but if we take bad actions, then we're compromising the opportunities to achieve higher reward in other contexts. So here we're considering 2 potential actions. So each action we call an arm. And for the sake of this example, each action corresponds with patrolling one area. And in my observation so far, I have a 50% probability of finding snares for patrolling each region. But if we also keep track of the number of times that we visited each area, this gives us an uncertainty interval that tells us our confidence of that this is actually the true value of poaching probability. And a common paradigm for online learning is this idea of optimism in the face of uncertainty. So we would prefer to take actions that have the higher upper confidence bound, because either we have the opportunity to accrue higher reward if the true reward actually is higher, or at the very least, we would reduce our uncertainty to do better in the future. So we would prefer to take action 1, even if the empirical mean is lower than that of 2, because its UCB is higher. So we take action 1, reduce our uncertainty, and continue until the UCB of action 1 is lower than that of action 2, in which case we'd switch over. But as Greg rightfully pointed out, one big challenge in this context is imperfect observation, and our likelihood of finding a snare really depends on how much effort we're spending there. And not only do we have for areas that we don't patrol, we have no observations. So this is standard with multi-armed bandits. This is known as bandit feedback because we only observe feedback of expected reward for actions that we do take. But we also have a different form of uncertainty here in which if we have a positive observation of finding a snare, we know that that's a true positive label. But if we don't, there's uncertainty as to what the true value is. And to just explore this a little bit in our data, if we look at the relative amount of patrol effort that is spent across the x-axis, across 25 different regions, so the probability of detecting snares is one line in one of these curves, then the probability of detecting snares increases with the amount of patrol effort, but with diminishing returns. So we don't want to spend an excessive amount of time in one area. There's kind of a point at which it's better to reallocate our resources elsewhere. So what this tells us is we need to think about not just which areas to patrol, but really how much time, how much effort to put in each region. And that's really what should govern our decision making. So now our action is not just a binary vector of which areas to patrol of length n, but rather a distribution over all n regions of how much effort to spend in each region, subject to our budget constraint of 40 hours a week. So maybe patrol for 3 hours in one region, 2 hours in another, and 0 in another. But now, based on this objective, there are several challenges. So one is that the action that we have to take is now this exponential size decision at each time step. So if we have n regions and some discrete number n of the amount of effort, so m could be 10 hours, we can spend up to 10 hours. The scale of our problem is this exponential m to the n number of possible actions that we could take at each time step. And it would just take an excessive amount of time to learn the expected reward for each of these combinatorial actions. And also because we are in this high stakes context where we really have to be performing well in the short term, we can't afford to explore excessively. So we also have to find ways to reduce our uncertainty as much as possible to reduce unnecessary exploration. So let's address these challenges in tandem. So first, thinking about the combinatorial action space, what we recognize is that there's really nice decomposable structure in our reward. So our reward from one combinatorial action is really just the additive sum of the reward at each region. So the number of total snares we find is really the number of snares for each region added up. And this means that instead of having to track expected reward of the combinatorial action, we can really break up the space into each region, n, and each level of effort, m, and track the expected reward of each of these separately. So now this reduces the number of actions that we're considering from an exponential m to the n to a linear m times n number of reward estimates, so greatly reducing our search space. And for the second challenge of not being able to explore excessively, what we can do is look at our reward function, which is this probability of finding a snare, and we can make a few observations about structure within this reward function. So one, pretty intuitively, it is monotonic. So as we spend more effort patrolling, we're never going to be less likely to find a snare. So that means we can transfer information that we've gathered for one level of effort to others. This function is Lipschitz continuous, so it is smooth with a bounded derivative that we'll refer to as L. And very intuitively, as well, the expected probability of finding a snare for no patrol at all is 0. So we know 1 point on this function is 0 patrol indicates 0 expected reward. So this all of this domain knowledge we can transfer into our learning process. And the way we do so is if we look at one region in the park, and let's say we have a good estimate for the expected probability of finding a snare at 3 kilometers of patrol, that gives us some understanding of what the expected reward should be at other levels as well. So now going back to this toy example, but here actions A and B correspond to not two different regions, but patrolling the same region at different levels of patrol. So action A is patrolling with 1 kilometer of effort, and B is patrolling with 3 kilometers of effort. And what this means is for any other level of effort, we have no idea at the moment what the expected reward is. So the expected reward could be anywhere within this green space. So this is really the space over which we are uncertain. But because, okay, so if we were to break up our, discretize our action space into 1 kilometer intervals, this means that the upper confidence bound of every action we haven't yet taken is 1. It's at the very top because we haven't explored it yet. So this requires us to collect very many samples in order to shrink those UCB estimates to take other actions. And this problem would exponentiate as we further discretize this space, because in theory we could have a continuous number of possible levels of discretization. So here's where we leverage the domain structure from our reward function. So first, think about Lipschitz continuity. We know that if we have a good estimate of reward at 1 level effort, that gives us some bound on the expected reward at similar levels of patrol effort as well. So Lipschitz continuity will help us prune our uncertainty space. So instead of having the whole kind of green region be the space of possible observations, we can really reduce the UCB estimates based on the observations that we currently have. We also have the fact that no patrol indicates no expected reward. So this combined with Lipschitz continuity is also very powerful in pruning our space of possible exploration. And finally, monotonicity guarantee tells us that whatever estimate we have at 1 level of effort gives us an upper bound on any lower level of effort as well. So that enables us to further reduce our uncertainty space. So all of these tools, all of this problem structure enables us to reduce the amount of unnecessary exploitation that we're doing so that we can move faster to effective exploitation. And another way that we can transfer knowledge is recognizing that each action, each arm is not some isolated unit in some kind of ether, but rather they correspond to physical locations in the real world. So that means that any insights, any predictions that we get for one region gives us some understanding of what we think the reward will be at other regions too, based on how similar these areas are or how close together they are. So we can transfer learning from one arm to another. And to just visualize this, so let's say this is some region 1 that we have these current estimates for, and there could be some other region that we haven't yet explored, region 2. So all we know so far is this assumption that 0 equals 0. But if we can quantify how similar regions 1 and 2 are, so let's say that their elevation differs by only 100 meters. So we can take whatever similarity function applies across these 2 regions to transfer our estimates using our Lipschitz continuity assumption. So we can say that the expected reward of arm of region 2 will only differ by at most delta from the expected reward of action 1, so that we're transferring with the addition of this plus positive delta, and that provides further estimates of what the upper confidence bounds of each of these estimates can be.
So question, should
yep.
You're describing this in very ORE terms, like constraints on the search space. Should we also be thinking a bit more like Bayesian terms, where you initialize the prior of one bucket based on the priors of other buckets and then refine and it'll convert to the right thing?
Potentially, but I think the way that we're approaching it is that it's not that we begin with one prior and then we only collect information for region 2 in isolation from region 1, but any further samples we get from region 1 will also like update our estimates of region 2 and every other region at every time step.
In a constrainty way, right? You say that, like, I'm seeing constraint bound, so you're thinking like samples from one put constraints on others.
Exactly. Yes. So we can reduce our upper confidence bound estimates of whatever we think that like with 95% probability, like the expected reward plus our uncertainty interval is at most this.
Got it. Thank you.
Mm-hmm. Yeah, and that's based on these assumptions of Lipschitz continuity and monotonicity. So all together, this gives us estimates of the expected reward for each region at each level of effort. And now to translate this to a decision that we should make per week, we use mathematical programming, ORE again, as Greg points out. So to take these individual estimates and combine this into a combinatorial action to take within every time step, our objective, similar to standard multi-armed bandits when we're using optimism in the face of uncertainty, is just maximize the sum of our UCB estimates. And again, we're able to do this because of the additive nature of our reward function. So we can just sum up all the UCB estimates for the actions that we do take and constrain this by a budget constraint. So the total amount of effort that we can spend is no more than B. And note that this problem formulation is fairly general. So here I've laid out like the simplest type of constraint, which is just the budget constraint. But we can also account for more complex constraints. So if we maybe say they have to go to a region, like they have to explore each sub-region within the park, they have to kind of like divide their effort equally across all of them. We can incorporate path constraints. So if they have to begin and end their patrols from a patrol post or any other specific location. So all of those additional constraints can be added to this mixed integer program in order to accommodate that. So it's a flexible model. And this overall approach we call Lizard, which is Lipschitz arms the reward decomposition. And to just tease a little bit of mathematical intuition for how this performs and the benefits that we'll get from taking this approach and integrating this problem structure compared to standard forms of online learning, for example. We have the following regret bound for this Lizard algorithm. And with regret, we're comparing how well our algorithm is doing, like what reward are we getting in comparison to some optimal action. So here we want regret to be lower. So smaller is better because that means we're closer to the optimal. And regret can be broken up into two terms. So we have the regret from the discretization error for so how much we're losing out by whatever discretization level we pick. And the second is the selection regret from not picking whatever the optimal arm is for that level of discretization. And with multi-armed bandits, the time horizon T really dominates. So that's what we look at. And each of these terms is discretization error is effectively on the linear O of T. And then the selection regret is sublinear on the order of root T times log T. So really the discretization regret dominates. It's going to be bigger than the selection regret. So in order to do better, we want to see how to reduce this term. And intuitively, what this tells us is that if our discretization level delta is smaller, then we're able to reduce this value. But smaller discretization means that we have to do more exploration. So there's that trade-off. And intuitively, what we want to think about is either if we have a longer time horizon or fewer regions or a bigger Lipschitz constant, then it makes sense to reduce delta and look at a finer discretization. And mathematically, what we can do is think about setting delta adaptively over time. So we start with like a very coarse discretization, and as we collect more information, then we can reduce delta and now go to a more fine-grained approach. So to make the math work out nicely, we have this schedule where every T number of time steps, we divide delta in half. So we're just iteratively subdividing our discretization in half and half again. So overall, this approach gives us, this adaptive discretization approach gives us this nice regret bound that is independent of the number of regions that we have. So there's no dependence on N. And this contrasts to existing approaches that focus only on the Lipschitz component of this work that does scale as the number of regions grows. So for the Lipschitz algorithm alone, we have this, as the number of regions gets bigger, we have the regret bound approaches a linear O of t, but we are able to stay at O of 2/3, regardless of what size n is, by combining this combinatorial decomposable action space with Lipschitz continuity. And we also have we also are able to evaluate this work empirically on data that we have from Shipak Wildlife Sanctuary, where here we're evaluating performance, so higher is better, and our algorithm gets close to optimal, especially within the early time horizons compared to existing approaches. So now moving on to the second stage of thinking about sequential planning. So the key question here is, what we've been considering so far is assuming that there is some general pattern to poacher behavior, and we have to learn what that is. And it might vary with seasonality. It might vary with the geography of the land, but it's going to be consistent over time, just stochastic. But we can recognize that in the setting, we are working against humans who are strategic and will have their own interest and don't want to be caught, and want to catch animals. So thinking about this now as like a reactive approach where poachers are observing what we're doing and reacting to that. So we began with looking at data sets from 2 parks in Uganda. And what we observed is that when rangers patrol more in one region, the probability of poaching goes down in the next time step. So there is this phenomenon of deterrence. They are reacting to our actions. And what this tells us is, therefore, we have to take a sequential planning approach, such as using MDPs to model this problem. But in order to bring in tools like Markov decision processes and apply reinforcement learning, we need a good model of the environment. But because our data is imperfect, we're not able to get a really strong estimate of what the exact behavior is going to be. So if we estimate that the amount of deterrence is some 17% reduction, we can't be too confident that the true value is 17, but we might be much more confident that the value sits somewhere between 12 and 23%. So now we relax our estimate into some uncertainty interval, and we want to do planning over that space. And what I want to pitch is using this objective of minimizing the maximum regret as our objective for robust planning. And let me talk through why I think this is a good objective. So let's say that the parameter over which we're uncertain is z. So z, let's say, can take on one of 3 values. And if we look at the best policy, train an optimal RL algorithm for each one of these parameter values, there's some amount of reward that we would get for the optimal policy with respect to each of these 3 settings. And we can also evaluate what the worst policy is. And then the space in between the reward of our optimal policy and the reward of our worst performing policy refers to this gap in decision quality. So this is really the space over which we have agency. We can find some policy that would put us somewhere in this green region. So now, if we were to take a single policy, pi1, and apply that to all 3 settings, it would achieve different reward based on the 3 settings. And the current objective that's often used for robust planning with reinforcement learning is maximizing the minimum reward. And here, the minimum reward is in this first setting. So we would think about how can we do better in this context. But what we see is that the ceiling is really low. We can only do a small increment amount better. So maximizing the minimum reward, or maximin, is overly conservative, and we'll focus all of our effort on this worst case scenario, ignoring the other scenarios because the reward is relatively higher there. But this objective of looking at regret will instead think about the decision quality that we have to control, and we can quantify the amount of regret for each setting and compare how well we're doing compared to the optimal. So we're doing this relative notion of performance based on what is possible. And now the setting with maximum regret is this third context. So trying to minimize our maximum regret is, I think, much more reasonable, and will focus on optimizing decision quality rather than this more conservative notion of just maximizing our minimum possible reward. So if you agree with me that this is a reasonable objective. So now the objective for our reinforcement learning policy is minimizing maximum regret. So finding some policy pi that will maximize over all of our uncertain parameters z, regret. And regret is defined with respect to some optimal policy, pi star, compared to the reward from our policy, pi. And this is a really difficult objective to solve for because pi is a sequential and continuous policy that maps states to actions. Our uncertainty space z can be many dimensions long and can also be continuous. So this is a large continuous action space. And furthermore, our regret objective depends on z. So as we perturb z, the optimal policy pi star will change, because every little change in z means that there's going to be a different optimal policy. So this is really a min-max-max problem. There's kind of like underlying maximization problem of finding the optimal policy. So this is a really hard and large search space. So this min-max regret objective has not been considered with RL previously, in part due to the difficulty. And to make this problem more tractable, we formulate it as a two-player zero-sum game that sets up the min-max problem as two players competing against each other. So we have a planner that's trying to find some optimal policy given an environment setting. And we have this adversary, which is nature, that's setting the environmental parameter, that's finding some transition probability that will maximize regret for the planner. So there's kind of some similarities with curriculum learning, because within each iteration, we're making the problem harder and harder with respect to which actions we've tried so far. And this iterative game approach enables us to iteratively search our large uncertainty space to find an optimal policy, instead of having to go through this exponentially large search space. So it just makes this search process more tractable. And we can also show that this approach will converge to within epsilon of some optimal strategy within a finite number of time steps. And the last thing I want to talk about is this deployment. Oh, sorry, Greg?
Yeah, so responding to the patrols. But it sounds like your behavior model is random, right? The poachers are just kind of like messing with the estimates of patrol effectiveness and not being kind of like fully rational kinds of agents, like, oh, sorry, fully adversarial. Is that fair?
Correct. Yeah. So we're saying that they're reactive, but they're not like, purely game theoretic. And the reason for that is because formulate this like with a game theoretic model requires that they have perfect observation of our actions. So we would plan some patrol and they would best respond to whatever our action is. But the challenge is, because imperfect observation goes both ways, like we don't have perfect observation of what poachers are doing, and they also don't have perfect observation of what we're doing. So within every month, they don't know exactly where we're going to go. And also poachers are, they're independent. There's many different poachers who are active, and they're not sharing information. They're not coordinating to develop like a holistic plan for where to attack. So even the problem for rangers, where they are sharing information, they do have this coordination element. It's really hard for rangers to even know exactly what poachers are doing. We can't assume that poachers have perfect observation or full observability or are perfectly rational as a result.
It makes perfect sense. So now, one thing that I then observe is your actual iterative solution is very much like an agent-based simulation. That's kind of, the perfect algorithm isn't feasible for the reasons you described. So you went for, what's called the planner, or what's called adversary kind of thing. But now I get the impression you can put any algorithm into both slots. You can put your imperfect adversaries in there. Under the idea that you have optimal policy under semi-rational adversaries, right? And same algorithm.
This is very much like a meta algorithm. So we can kind of instantiate each component with whatever, and this is just what we've formulated as like the best instantiation that we think for this problem setting. But I completely agree with you.
Cool, thank you.
Depending on whatever model we think makes sense for the environment, we can adapt accordingly.
Yeah, and I guess your model of poachers, like the one you actually want, is these smart, not very adaptive kind of adversaries, not worst case adversaries, but really just.
Exactly.
And I guess the target would be, you're assuming in your formulation, you assumed their impact is on randomly reducing accuracy, whereas here it's going to be random evasion, I guess.
Yeah, I want to call it random, because it is governed by how much action we took at the previous time step. So that's
Right.
this model of deterrence, that when we patrol a certain amount in 1 month, in the next month, if we patrol really, really intensively, then poaching goes down more dramatically than if we didn't patrol at all.
So to what extent can you make, like I'm actually thinking you're learning the behavioral model of the poachers by observing
Right.
them, right? So
Right.
that's actually part of the optimal algorithm, right?
Yes. Yes. Well, that's kind of the first stage. Like first stage, we like build this model, and then with this model, we now plan. We formulate our model, and now we plan with respect to this model. So it's kind of a two-stage process. Like the behavioral learning comes first, and then we do the planning.
Right. And the other thing I'm observing, this same algorithm is relevant for detection of wildlife in the wild because they run away from observers, right? So now you have the reaction is maybe not that calculated, but it's pretty calculated. They know where
Yeah,
not to be, right? So if you want to document biomass or animal life,
absolutely.
it's
Yeah,
this.
absolutely. Yeah. So I think these types of sequential planning tools, like thinking about the environmental settings with dynamical models and applying sequential planning tools, is really a good fit for many environmental challenges, but is, I think, really underutilized. Like oftentimes you just apply static models, static policy optimization solutions, and then we might, if we're good, we might a year later like update with a new static model based on the new data that we have observed, but it's not really planning ahead. It's not doing like look aheads of trying to think what would the impact of our actions be. So
Got it.
that's what I think
Maybe
is.
one more thing, because it smells so much like other problems. Any kind of economic intervention has the same shape. I'm thinking you have farmers, here's the incentive to plant this way as opposed to that way, and they respond and they adapt rationally by extracting as much money from the planter as possible. To
Yeah.
what extent is this like a template for related like mass coordination problems, or to what extent is this more like for your evasion problem?
Yeah. So with max coordination problems, again, it just depends on how they are responding. So if they are like perfectly rational, then you now have like a two-player game, a stack over game, with multiple what's it called? Multiple like second players. So there's like the policymaker, somebody who acts, and then a bunch of different farmers who best respond accordingly. But then there might be, it depends on whether or not there's interaction effects between the farmers. Like that would really change.
That makes
That would
sense.
make the problem
Got it.
potentially more complex.
Cool. Thank you.
Of course. Okay, so the last little bit here is, after we've taken some action, we want to understand its effectiveness. And ideally, we want strong causal conclusions. So I mentioned before that this last paper was on reinforcement learning, was motivated by observing deterrence. And for that study, we had looked at it correlationally. We had just kind of studied the data, but didn't apply tools from causal inference or quasi-experimental design to it. But we were really interested in understanding this question more broadly, especially because it's kind of an open question within conservation. Some people think that deterrence is like the main driver of ranger efficacy. So aside from the direct impact of physically removing a snare, we have the indirect effect of discouraging them from coming back in the future, and that deterrence is so much more prevalent. But other people think that there's so many snares and rangers are only able to remove a small number, like 10% of all the snares. So then it doesn't really do anything. There's no long-term deterrence. So we're really interested in trying to answer this question of the impact of patrolling at one time step on poaching behavior in time t+1. But it's really hard to get a strong causal conclusion for these types of questions because, as we know, correlation does not equal causation, and the gold standard for causal effect estimation is a randomized controlled trial, which is often not feasible in these kinds of high stakes contexts because the opportunity cost is very high. So if we randomly picked a series of areas to not patrol at all for a few months study, that area might just become inundated with poaching, and we might have just kind of like significantly high losses. And the second challenge is, as we've discussed several times now, we have imperfect observation. So snares are really hard to detect. Here's a photo of a snare in Uganda. You can barely see, like in this grass. And we know that our ability to detect a snare is not equivalent to the true presence of a snare, and specifically that there's uncertainty in our negative labels, whereas any positive labels we see does give us like a definite, does give us certainty that there is snaring present. So in our paper, which is currently under revision, it applies machine learning with causal inference to overcome noisy data and unobserved outcomes. So what we do is leverage the fact that a previous work that we did implementing a field test in Murchison Falls National Park, where we had rangers do the same thing as Cambodia, patrol a random series of high risk, medium risk, and low risk areas. That this 5-month field test actually changed ranger patrol patterns because we had them patrol areas that were infrequently patrolled in the past. So that 5-month field test served as a shock to the system. And we can look after the shock ends, after the field test ends, we can see how poaching behavior changes between the areas that were part of the field test that were patrolled more versus areas that were not in the field test that were patrolled less. And overall, the effect estimation that we're able to get is for a typical site in the park that has about 21% probability of being poached. If we patrol an additional kilometer, then that poaching probability drops significantly to about 12%, which is a 45% reduction in the probability of detecting snares. Or sorry, a 45% reduction in actual snaring. And we feel like this result is very significant in being able to help inform policymakers of the value of ranger patrols and give justification for park managers and NGOs to come to funders and say, this is work that we need to continue to support.
So this is regression discontinuity design, right?
This is we set it up as it's not we set it up as two separate periods. So there's the shock period, which is the 5-month field test, and then there's like the 5 months after the field test. And we're looking at we used matching to break up the areas of the park to areas that are patrolled more than usual during the field test to areas that are patrolled less than usual during the field test, and then we compare the poaching outcomes in the more patrolled areas versus the less patrolled areas. So it's not quite regression discontinuity because there's not like a time step, but rather we're kind of synthetically creating treatment and pseudo treatment and pseudo control groups based on this shock.
So yeah, it's more like a diff and diff where you have like matching areas, but now because it's a contiguous park, poachers may move from place to another. So how do you deal with the interactions between the areas?
Absolutely, great question. So thinking about possible displacement from one area to another is really hard to just get causal conclusions of looking at differences, and looking at displacement is very, very difficult. But because so if we kind of go back to if we go back to what the field test looks like, we see that this is an example from Cambodia and Uganda is different, but the areas that were patrolled more are fairly spaced out from other areas. So the sites that end up being our treatment sites versus the sites that end up being our control sites are pretty spatially set apart. And therefore, we think that if there is displacement, it's not really going to change the estimate that we're getting across treatment and control. So there might be displacement to other sites that aren't part of our study, but it's not going to spill over from our treatment versus our control sites.
That makes sense.
Yeah. Here I might have, no, I don't have. Yes, I do. Okay. So I do have I have this map of the pseudo treatment and control sites from Murchison Falls National Park in Uganda. So everything in white are areas that are patrolled kind of like as typical. And areas in red are the areas that were patrolled more than usual during this 5-month period. And in blue are the control sites that were patrolled less than typical. So here, this map of red dots are pseudo treatment sites, and this blue map are pseudo control sites. And it's hard to tell because they're not kind of laid on top of each other. But typically, in this context, we think that if there is spillover, it's going to be fairly localized because poachers come from adjacent villages. They oftentimes like walk in by foot or they just drive in. It's a large park, so it takes time to cross. So we think that and rangers also think that any potential displacement would be very localized, so they won't move very far. And then because the treatment sites are not directly close to the majority of control sites, any potential displacement would go from treatment sites to like a neutral site or control site to a neutral site, rather than moving across these two groups. So we still think that our effect estimate is robust.
Interesting. So then one more like extrapolated question. If I'm thinking of forest protection, where I want to say something like additionality of my interventions, because I had the same problem. If I protect one part of the forest, logging in this case might move to another one. So how do you evaluate, like, can you adapt the stuff to evaluate additionality of various ecosystem conservation kinds of activities?
Yeah, absolutely. And I think the approach that we tried to build in this paper could be applied broadly to settings with imperfect observation. But the challenge is that in real life, it's fairly rare that we have a kind of shock that introduces exogenous variation in the system. So this field test, we randomly selected a subset of high risk areas and randomly selected a subset of medium risk and low risk areas. There's that element of randomization, plus the fact that 4 or 5 months, patrol behavior changed and then went back to usual because we were no longer implementing this test. So like that type of natural experiment is typically more rare. But I think these questions of effect estimation are very valuable. Okay, and then just very quickly, I mentioned at the beginning older work that we did on predictive modeling in this context, just try to predict poaching risk, and based on the explosion of new approaches and diffusion models and other forms of supervised learning. We also tried applying diffusion models to poaching prediction, where now instead of doing predictions individually across each region in the park, so looking at a 1 by 1 kilometer region in isolation, just based on its covariate features. Now diffusion models enable us to think about like spatial correlations between adjacent units of poaching risk, and in this approach that's currently under review, we look at the kind of graph model of different sites in the park, and we develop a flow matching algorithm that, instead of initializing our diffusion model through random noise, we initialize our model based on like a naive prediction using logistic regression of poaching risk. So we have this kind of like first stage where we're training a naive logistic regression model of poaching risk, and then we initialize our diffusion model with this. And our model separates out the problem of predicting poaching probability with predicting detection probability. So really looking at this challenge of imperfect detection in separation. And altogether, this gives us the predicted probability of observing poaching. And our approach, it's hard to, I should have made this a little bit more clear, but our approach gives us about a 7% improvement in the area under the precision recall curve compared to a number of other baselines.
Well, question, it looks like you're diffusing this over space? Over the park?
Yes, exactly. Okay. Yes. So this is like the spatial connections, looking at adjoining areas. Yeah. And one more thing that I just wanted to mention is also recognizing that, Nibod?
Oh, hi, Lily. Question. So I don't think you mentioned looking at an MDP earlier. Was that also for predicting probability of poaching, like the diffusion model?
So the diffusion model is moving back to the static context. We're just trying to predict
Okay.
risk. We're not.
Okay.
This is just thinking about how good of a prediction can we make in a static context.
Mhm.
And then we could combine this with some estimate of poacher response, such as like the model for deterrence that we have. But
Mhm.
this component is purely like a static prediction problem.
Oh, okay. So this is a purely a static prediction problem. Okay. And another question. So were you able to so earlier you mentioned RL-based approaches, and also the multi-armed bandits. Now, so full disclosure, I was commuting at the time, but were you able to bake in the prediction problems from the static prediction into using it as like the unknown dynamics in the RL problem, like to develop perhaps any optimal control solutions?
Yes, absolutely. So like I don't have it written out here, but in our model of deterrence here, we have
Mhm.
like what is the baseline like poaching probability here, and then what is the amount that this will reduce based on what actions were taken in the previous time step. So we take that kind of static prediction problem, and then we try to estimate the amount of change.
Oh,
by act.
thank you very much.
Awesome. Okay, so just in the last minute, just wanted to quickly mention that everything with respect to nature conservation, to climate, with sustainability, really exists within a broader like political ecosystem. So I also have some work that's thinking about some of the sociopolitical implications of AI for biodiversity, working with biodiversity data. And this paper, that's a policy form in science, looks at the biases that exist within biodiversity data that is being used currently to inform the global biodiversity framework. So it's very important that we're able to like recognize and quantify the imperfect nature and the entrenched social and political inequities that are present in the data that we're using to make these kind of like high stakes multilateral decisions. And then also thinking about the broader implications of machine learning for environmental science. So I just wanted to plug these papers led by my colleagues Millie Chapman and Caleb Scoville. But that's really what I had to share with you all. Thank you so much, and thank you very much to my collaborators who I worked with on this. But very excited, I would love to learn more about what you all are doing across Alphabet, and if there are opportunities to bring in some tools from decision-making, online learning, intervention planning, reinforcement learning for the kinds of problems that you're looking at, I would always be happy to chat.
Well, fantastic. Yeah, thank you very much. Thank you for all the valuable information. And yeah, looking forward to more contacts. Thank you.
Of course.